All right, so I decided to break this up in a separate video. I was having some technical problems, and so that's okay, right? Well, maybe about 20 minutes is about enough of me talking in a row anyway. So, a couple more problems here. Let's keep looking through this. There's this problem here again. Copy down, stop, do it on your own, come back, check. One thing I didn't mention last time is, or maybe I did, I don't remember 100%, right? When we're doing these multi-step synthesis for organic chemistry, the wonderful thing about this is that there are multiple correct ways of doing it. Some ways are more elegant than others, some ways are better than others, but, the answers that I give are not the answers, right? They're not the only answers. There are other ways of doing it, and it's good to kind of use your own creativity to come up with something. In fact, to kind of build off of that idea, if you guys wanted to go back and try and think of another way of coming up with the answer, right? Another unique way of coming up with the answer, that's fantastic practice, right? So for this problem here that we're going to go through, in fact, really only for this problem here, right? You could come up with multiple ways of doing it, right? So go do it. See what you guys can come up with, right? It's great. It's a great practice for you guys to try and do that, all right? So anyway, sorry, just to finish that thought, actually, the counterpoint to that is there's also multiple wrong ways of doing it. And so if you guys come up with another way and you guys are like, well, I'm just not sure, I'm not sure this would work, or, why would this work or why wouldn't it, send me an email, scan it, snap a photo, send it to me, and I'll be happy to take a look at that stuff and, see if I can help you guys out along the way, right? But anyways, let's take a look here. So again, the most important thing you can always do is to stop, think, to look, to assess, right? Okay, so we start out with 3 carbons, and then we end up with 5 carbons, okay? That chlorine that we have at the beginning doesn't necessarily mean it's the same chlorine there at the end, right? In fact, it's highly likely that it isn't, just off of initial assessment, right? So we have 3 carbons, we end up with 5, and we have to put a chlorine there at the end, okay? So this is another subtle clue here, right? This is another little clue. So if we're increasing the chain length of an alkyl by 2, a really good way of doing that is to throw in an epoxide at some point, okay? Is it the only way? No, of course not, right? But if I want to add 2 carbons and kind of make sure I have a functional group left over at the end, epoxides are a great way of doing that. So for this problem, there's no restrictions given. It just says make these from that. So we can use whatever we want along the way. So what I'm going to do, right, if I want to add an epoxide to this, right, with those 2 purple carbons there, I can't just mix these 2 together, right, and then have it make something new, right? That's not going to do anything for us, right? An alkyl halide plus an epoxide is going to do nothing, right? It's, an alkyl halide's not acidic or basic, it just is, right? So we're going to have to come back and do something with our initial alkyl halide and then add the epoxide to it. Got it? All right, so let's do that. So how can we make our alkyl halide acidic? Well, we could turn that chlorine into, an alcohol, and then put that under, acidic conditions with an epoxide, and we could do it that way. And that would certainly be good practice for you guys to see if you can come up with that, right? But I'm going to go the other route and make this basic instead. Okay, so how can we make an alkyl halide into a good base? Well, the best base that we can make with it, the easiest, right, is if we Grignard this up, right? So if we turn this into MgCl. And the easy way to do that is we just throw some Mg in there. We would need some kind of ethereal solvent, so diethyl ether, THF. We'd need the right equivalents of magnesium, and we'd need some iodine and all this kind of stuff. in reality, you know, we would throw in some magnesium and scratch the surface and probably some iodine and stir it and all this. Okay, we're doing chemistry on paper. For me, it's just fine. You guys throw in magnesium. I know what you guys are trying to do, right? You guys are trying to make a Grignard. Now remember, with a Grignard, it's a powerful base, an extremely powerful base, right? And so if we now take our nice powerful Grignard there and put this under, oops, and throw in some of our epoxide, right? So powerful base, epoxide, ring opening. It's going to attack the less substituted side, except in this case, both carbons of the epoxide are equivalent, so it can attack either one. And so remember, when we're dealing with Grignards, you always got to come back with, you know, an acid workup or a water workup, or either way is fine. You know, we'll shake things up because it's a Monday and use acid this time, right? Okay, so if we do that, right, then what we will end up doing is the Grignard will attack the epoxide, and we will end up with this. Got it? Can you guys do that mechanism? Yep. Should you guys be able to do that mechanism? Yep. All right. Now the age-old question, how can we turn one functional group into the other? Can we turn an alcohol directly into a halide? And the answer is yep. All right. So there's, again, multiple ways of doing that. See if you guys can think of multiple ways. You know, if we were in the lab and we were practically doing this, I would use my good old buddy SOCl2 thionyl chloride. And thionyl chloride's best friend is its buddy pyridine. And wow, that was impressive. Okay, pyridine's in there to help things kind of move along. You can look up the mechanism for what the pyridine does with thionyl chloride. It's not, I would say on paper, it's not too important, right? Now, this goes back to a question, though, of does right, we have a primary alcohol, are there ways we can't turn a primary alcohol into an alkylate? And the answer is yes, right? So remember, we have to avoid making carbocations, right? It's just not going to happen. So just throwing HCl in there wouldn't really be that efficient of a method of doing this, right? That would be a very, 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 very slow reaction, and there's a couple other problems with it, right? But we could throw HCl in with some zinc, and that might make things a little bit better. But thionyl chloride would probably be your go-to choice if we wanted to practically do this here, okay? So there we go. So if you're working through a problem and you see you have to add 2 carbons, you know, an epoxide is a great way of doing that, okay? Cool. Alrighty. So now we start out with this aromatic ether, and we end up with an aromatic ether. Okay. Again, stop, look, assess, try and work it on your own, think about it, work it through, all that kind of stuff, right? So one of the common pitfalls that I see with students is that, let me just change colors here for just a second, just to make an argument. They assume that everything in black here, right, has to be exactly the same as everything in black there, right? That everything's retained. That every carbon that's in black has to be retained there towards the end. And so what I mean with that is then, you know, oftentimes I'll see students say, well, I just need to add something there. Well, I mean, maybe, right? Maybe you could do that. That's going to be a little bit challenging to do in this case. But in reality, right, let me just kind of take this back to the beginning. In reality, if we're dealing with an ether, right, it'd be far better just to kind of look at this and say, well, I can maintain that group right there, right? Because what I'm really doing is just swapping one part of an ether for another, right? I am making an asymmetric ether and turning one asymmetric ether into another. And so we talked about this quite a bit in our lectures, and the book talks about it quite a bit also, right? When we have to deal with asymmetric ethers. Okay? So the first thing I want to do here is I want to break this ether apart. I want to break this ether apart into the red portion, right? That stuff over there. And I want to take the green portion off over here. So I want to cleave this ether, right? And a good way of doing that is under acidic conditions, and we want a pretty good acid with a good nucleophile and all this other kind of stuff in there. And so kind of our go-to choice, or what I would recommend in this case, is to use our good old buddy HI, right? And if we go through and we do the mechanism, which you guys should be able to, right? What we end up with is, we end up with this, right? Plus, what we will also end up with is that right there, right? And so that'll be a clue for you guys if you don't know the mechanism on the top of your head, right? See if you guys can go through and make that product there. Now, the methyl iodide we don't really care about, right? That's not going to be something that we need. But this we can use, right? So let's do that. So now the question is, how can we turn an alcohol into an ether, right? And so here we go back to our Williamson ether synthesis. In our Williamson ether synthesis, what we needed to do was deprotonate our alcohol and then add in an alkyl halide. And so what I would do is I would add our good old buddy NaH, right? And then add in some kind of alkyl halide, right? Ethyl bromide, ethyl iodide. The ethyl iodide would probably be better in this case, right? And then if we do that, right, our product here would be this, okay? Where, let's see here, purple, right? Those are my carbons right there. Sodium hydride here, right? Strong base. Good for deprotonating alcohols. And so this is a classic Williamson ether synthesis setup here. Strong base over some kind of alkyl halide to make an asymmetric ether. Okay? So why did I like this problem here? Well, it's because it's kind of what I talked about there at the beginning. One of these classic traps is, okay, all the carbons are the same from the beginning to the end. Well, don't limit yourself to thinking like that, right? I'm not saying go out of your way to swap everything out, but think about what functional groups you have, assess how we can transform one functional group into another, right? And see, the kind of conditions and know the kind of conditions we need to do that. Okay. So my clue here is I knew I was making an asymmetric ether. There's really only one way that we learn to make an asymmetric ether, and that's the Williamson ether synthesis. So I had to know that I had to have an alcohol present, and then all I had to do was cleave my ether. Okay. So this is one of those cases where we really don't have too many options about how to make this, right? So there isn't, I could not, for this one I can't really say go back and come up with another way of doing it. You might be able to, although, the other ways you have of doing this would have its, significant problems. But, maybe you guys could come up with something clever. And as always, send me an email and let me know, and I can give you guys my thoughts about, your multiple steps there. Good? All right, so this was a pretty short video, right? Not too bad. I'll continue making some of these videos along the way, not to overwhelm you guys with stuff that I post online. But as always, and I keep repeating this because it's so true, if you guys need some help, please reach out to me in whatever way. You guys have my email, right? I'm on Teams. You guys can drop me a message on there, and I'll get back to you guys as soon as I can, okay? All right, I'll see you guys next time.